Hello and welcome to the next lecture of the transistor series. Here we are going to discuss about the stability factor of self-bias. In our previous discussion, we have done the circuit analysis of self-bias or voltage divider bias or potential divider bias. And there we have just considered the end result of the stability factor. Now in this lecture, we will derive the stability factor for self-bias. So this is the self-bias circuit, and earlier we have analyzed this circuit. Now a different kind of analysis we shall be doing here, and we'll be finding the Thevenin's equivalent circuit for the self-bias circuit. Now in Thevenin equivalent circuit, those who have not studied Thevenin's theorem, for them to make it easier, this entire network will be reducing and considering this as one resistor and as one voltage source. Now the voltage source will be considering as the input section of the transistor as the voltage drop across the R2. So this resistor, whatever voltage drop we have, so that we consider as a voltage source. So here we have this voltage source E0. So if we try to find the value of E0, so E0 will be equal to the drop across R2. So the total voltage supplied is VCC, and if we use this voltage divider network, then we can write that E naught is equal to VCC into R2 divided by R1 plus R2. So this is the value for E naught. Similarly, R naught is the equivalent of R1 and R2. Since we are reducing this network to a single resistor, so we can write R naught is R1 parallel R2. So we can write it as R1 into R2 divided by R1 plus R2. So with this condition, further we'll be analyzing this Thevenin equivalent circuit of the potential divider bias. So if we consider the input loop and if we apply KVL here, so what we obtain is E naught minus drop across this, that is IB into R naught minus this drop VBE minus another drop we have here, so IE into RE. So if we add them all, we'll get 0. That is what the Kirchhoff's voltage law says. So if we rearrange this, we can write it as E naught, that is equal to IB into R naught minus, we are taking it in this side, so we'll be having it as plus VBE plus IE. If we divide this IE, we can write it as IB plus IC. So we know that in transistor, the emitter current is the addition of or summation of IB plus IC into the resistor, emitter resistor RE. So let us call it equation number 1. Now let us differentiate equation number 1. Differentiate equation number 1 with respect to IC. So what we obtain is dE naught by DIC, that is equal to DIB by DIC, and here we have the coefficient as R naught plus here we have coefficient as RE, so RE into DIB by DIC plus RE DIC divided by DIC plus for this one we have DVBE divided by DIC. Now, interesting point, we can note that E naught is a battery DC current. So we can consider this as a constant, and VB, this is also constant for different kind of transistor. For silicon transistor, we have VB as 0.7, and for germanium transistor, we have this as 0.3. So this is also another constant. So these things will get as 0. Then this equation we can rewrite as 0, that is equal to R naught dIB by DIC plus RE dIB by DIC plus DIC will get 1, so we are getting it as RE. So further, if we rearrange this equation, we can write as dIB by DIC, that is equal to minus RE divided by R naught plus RE. So call it equation number, say this is equation number 2 and this is equation number, say 3. So we are getting this value. Now we shall be utilizing this value, and we know from the general expression of stability factor, S is given as 1 plus beta divided by 1 minus beta dIB by DIC. But this dIB by DIC we have found here as minus RE divided by R naught plus RE. So we shall be replacing this from equation number 3. So let us call this equation as 4. So replace dIB by DIC from equation 3 to equation 4. We can write S is equal to 1 plus beta divided by 1 plus beta into RE divided by R naught plus RE. So further, if we take this R naught by RE to the numerator, then we can rewrite S as 1 plus beta, that is equal to R naught plus RE divided by R naught plus RE plus beta into RE. So this is the expression for the stability factor of self bias technique. Now in this equation, we can further divide this numerator and denominator by RE. So we can further reduce this expression as 1 plus beta into 1 plus R naught by RE divided by, so here also we'll get 1 plus beta, for this case we get beta plus R naught by RE. So now this R naught by RE, this is an important factor, and if we can make R naught by RE much less than 1, then here we can ignore this term, and here also we can ignore this term, and as a result of that we can obtain S equal to 1, so which is an ideal value of S. So here some points we need to note. So first of all, if we can make R naught by RE very small, then we can get the ideal value of S, that is equal to 1. So it sounds good, and here we will get the maximum thermal stability. But to achieve this value S equal to 1, it is not so easy. There are some constraints. Suppose if R naught can be made small by making R2 low, but if we can make R2 low, then lots of current, huge current will be drawn from VCC, and this will put the restriction on R naught. Similarly, we can make Re greater. Now, if we can make Re greater, then we need the higher value of VCC to maintain the proper zero signal current. So, these are the constraints of making R naught by Re very small. However, being an electronics engineer, being a designer, we can choose some optimum value of R naught and Re so that we can keep the S small and it may be achieved around 10. So that will be a good value of stabilization. So here we end our discussion. Thank you very much.